Virtually all industrial processes make use of gases and flowing liquids. To better understand these processes, operators need a basic knowledge of their operating principles. Compared to solids and liquids, the molecules of gases are spaced far apart. Also, there are virtually no cohesive forces between the molecules to hold them together, so they can move around freely. As a result, gases do not have a definite shape or volume. To keep their free-moving molecules from escaping, gases are normally stored in sealed containers. The temperature and pressure of a contained gas are directly related to the molecular motion in the gas. In general, temperature is the relative hotness or coldness of a substance. But at the molecular level, temperature is a measure of the molecular kinetic energy of a substance. Kinetic energy is the energy of motion, so temperature is related to molecular motion. Now, pressure is the amount of force exerted over a given area. Let's consider a particular area of this container. The pressure exerted by a gas results from collisions between the molecules of the gas and the walls of the container. If the number of collisions increases, the pressure also increases. This can be accomplished by compressing the gas or by increasing its temperature. For example, if the temperature of the gas increases, the kinetic energy of the gas molecules also increases. In other words, the molecules are moving around faster. This also affects pressure. For a given area of the container, there are more collisions between the gas molecules and the container walls, so the pressure also increases. In a contained gas, the properties of temperature, pressure, and volume are related. If a change occurs in any one of these three properties, the change will affect one or both of the other two. The ways in which gas temperature, pressure, and volume relate to each other have been formulated into three laws: Boyle's Law, Charles's Law, and the General Gas Law. Boyle's Law deals with the relationship between the pressure and volume of a gas. Boyle's Law states that at a given temperature, the pressure of a gas varies inversely with its volume. So if the volume of the gas decreases, its pressure increases. If volume increases, pressure decreases. We'll use this gas-filled container to illustrate Boyle's Law. We'll assume that the temperature of the gas doesn't change. The pressure in the container is related to the number of collisions between the gas molecules and the walls of the container. As the molecules collide with the walls, a force is applied over the surface area. With less volume, the gas molecules are squeezed into a smaller space, so there's less space between the molecules. As a result, there are more collisions between the molecules in the container. With more collisions in a given area, there's an increase in gas pressure. While Boyle's Law deals with pressure and volume, Charles's Law deals with temperature and volume. According to Charles's Law, at a given pressure, the volume of a gas varies directly with its temperature. That is, as temperature increases, volume increases. As temperature decreases, volume decreases. When the gas in the balloon is cooled, the volume of the gas decreases. As the volume decreases, the balloon shrinks. If the temperature of the gas in the balloon is increased, the volume of the gas also increases, so the balloon expands. We've seen how the pressure and volume of a gas react at a given temperature, and we've seen how the temperature and volume of a gas react at a given pressure. Now let's see how a gas reacts when all three properties are allowed to vary. We'll use this piston and gas-filled cylinder to illustrate the relationship. If a gas is confined in a given volume, and then the volume is decreased, there are more collisions between the gas molecules and the cylinder and piston. This produces an increase in gas pressure. If the volume of a gas decreases, the temperature of the gas increases because there's more molecular motion in a smaller area. This is a basic operating principle in an air compressor. Air is compressed into a smaller space. As the volume of the air is decreased, its pressure and temperature increase. If the temperature in an air compressor gets too high, it can lead to serious operating problems. To keep the temperature of compressed air from getting too high, air coolers are typically used with air compressors. One way to express the relationship between gas temperature, pressure, and volume is in a formula known as the general gas law, or ideal gas law. According to this formula, pressure times volume divided by temperature equals a constant value. This formula requires absolute units for pressure and temperature. Whenever there is a change in one of the three variables, pressure, volume, or temperature, the remaining two variables will change so that the value of the constant doesn't change. In this topic, we looked at some of the important properties of gases. We saw how changes in one gas property can affect others, and we looked at various gas laws. Take a minute now to do a couple of practice questions. If the temperature of the gas increases, the kinetic energy of the gas molecules also increases. In other words, the molecules are moving around faster. This also affects pressure. For a given area of the container, there are more collisions between the gas molecules and the container walls, so the pressure also increases. If the volume of a gas decreases, the temperature of the gas increases because there's more molecular motion in a smaller area. Many plant pressure measurements are based on atmospheric pressure, so operators need to be familiar with the basic principles behind atmospheric pressure. The atmosphere, or air, is a mixture of gases that surrounds the Earth to a depth of several miles. The air has weight because gravity pulls the air toward the Earth. The weight of the air exerts a pressure on the Earth's surface. This is what we call atmospheric pressure. Atmospheric pressure is related to height or depth. That is, the pressure of the atmosphere varies with the height of the air above the Earth's surface. For instance, atmospheric pressure at sea level is greater than atmospheric pressure at higher altitudes. At sea level, standard atmospheric pressure is 14.7 pounds per square inch, or psi. At higher altitudes, there is less air pushing down, so the weight of the air is less, and the pressure of the air is less. We can show how atmospheric pressure is measured with an illustration. This is a barometer that has a sealed tube filled with mercury and a bowl. When the bottom of the tube is unsealed, mercury flows from the tube into the bowl. The weight of the column of mercury exerts pressure, and the atmosphere also exerts pressure.